are not changing, are the same. This is what continuous. Now we want to give another topology, aim to define a topology on X satisfying this condition. Satisfying a topology called, that topology we want to call tau omega, satisfying the following condition. Tau dash any topology on X such that F belongs to X dash imply F from X, this tau prime to R is continuous. Only please see this carefully. Given topology induced by the norm, that you are denoted by tau suffix norm. What is our aim? To define a topology which we are calling tau suffix omega on X, that is going to be the smallest topology on X, satisfying the condition that whenever F belongs to X prime, the dual space, set of all continuous linear functional. Now already we know that F from X tau norm to R is continuous. Now this is another, suppose this is another topology on this X tau omega to R is continuous. But what we need is tau omega is smallest such topology. That means what is the relation between tau omega and tau prime? Tau omega should be smallest. That means tau omega is a subset of tau, not tau prime. Then this it should be for every, for all F in this condition should be satisfied. Okay. This implies we want smallest such topology that exists, that is called the weak topology on X. Now we have a topology which we call it tau omega. We have to prove such a topology exists. That topology is called weak topology on any non-linear space. Now we can talk about compact. Compact with respect to this topological space X, comma tau omega. Compact in X tau omega is called weakly compact. That's what we need. Okay, this clear? Okay, can you say what is the relation between tau prime and tau? Tau prime is some topology. Okay? On X such that F from X tau omega to R continuous. Can we say anything? Can there exist larger topology? Even it can be. Can you give some very large topology? Large topology useless for us because we are searching for a smallest. If we
discrete topology is
already, suppose the tau prime is discrete, whatever may be the function, you take any open set, inverse image is a subset of X, topology is discrete topology, means every set will be open, then this function will be, whether any function in particular, this type of F belongs to X prime also, it will be continuous. So, but what we want is, that's such a, we want the smallest topology, so that whenever the topology tau dash is such that for every F in X prime, X with respect to tau prime to R continuous should imply tau omega is a subset of tau prime. In particular, it will be subset of tau also, tau norm, because there also it satisfies F belongs to X prime in already f from x tau norm to r is continuous, but tau, that means tau omega will be subset of tau norm. Okay, so this much enough, at least to have an idea. This we will be using. That's why to use Jones lemma, we need this compactness. We will be using compact. What is important is compact if and only if it has a collection of closed set which has correct using some intersection property. Compact if and only whenever it is a collection of closed set which has finite intersection property, then it is compact. That we will be using, that type of thing. Okay, so it's fine. Any doubt? Please, this is very important, at least to, even if it is not very advanced, but that's what, but this is a part of metric topology, though not very advanced, but at the same time not only Cauchy sequence and convergence. Okay, any doubt? Okay, okay. Now this will come back tomorrow when we discuss about non-expansive math. Now again, to justify the topic, we have already discussed. Due to time, I will restrict to, we have X complete metric space. Complete metric space. Every Cauchy sequence in X converges to an element in X. A comma capital B, non-empty, closed subsets X. Almost like contraction, we define T from A union B to A union B, satisfying the following condition. T such that means it satisfies the following condition. 1, T, every element in A goes to element in B. Every element in B goes to element in A, and distance between T we are using, no? Tx comma Ty less than or equal to, there exists K, 0 less than or less, what is important is less than 1, non-negative and less than 1, K time. Okay, here you have to put some condition. Which condition you like to put? For all xy in A union. Suppose I write for all xy in A union B, will it be a new result? Suppose you write this condition for every xy in A union B, then what is A union B? A closed subset of a complete metric space, or A closed B closed, mean A union, finite union. A union B is a closed set. So in place of X, say our metric space Y equal to A union B. Subset of a metric space also a metric space. Closed subset of a complete metric space is complete. So A union B is complete. Correct? A union B is a complete metric space. So T from A union B to A union B, satisfy for some K 0 less than or equal to K less than 1, satisfy this contraction. Then what it says? It has a, that is nothing but Banach contraction theorem. Okay? Okay, now also it is going to be Banach contraction theorem. Okay? And tell that y for all x in A, y in B. See here, when xy both are in xy both in A or xy both are in B, we cannot write this. Only distance between tx, ty less than or equal to k time distance between xy only when x is in A, y in B. It is nothing great, just it is in a way some simple way of, we should not use okay. Right now we do not, this condition is there. What is that? So many times we discussed the Kautz iteration. What essentially we use? Start with any x naught from A. I mean x naught from the domain. It may be capital X if it is mapped from x to x, in this case A union B. X naught from A union B means x naught is in A or in B. Then what is Tx naught? Suppose x naught is in A, Tx naught is where? B. Tx naught, T of T, that we call it x1, like Picard's iteration. X naught belongs to A, T of x naught we call it x1, that is in B. Again T of x1 will be in A, call it x2. T of x2 will be x3, call it, that will be in B, and so on. So that means what? X naught, we iteratively, if we define n, xn may be either in A or B by induction. Assume that we are able to define x naught x1, assume that we have defined x naught x1 xn, we should be able to define xn plus 1. Xn is in A, then xn plus 1, T of xn will be in B. It is in B means xn plus 1 A. So we can define inductively. So what type of sequence we got? x2n is in A, x2n plus 1, all the odd term will be in B. Even term x naught, x2, x4 all in A. What type of sequence this? Using this condition. The defined sequence xn. What type of sequence? That's nothing new. Here no, absolutely new. What type of sequence xn? Pardon? We use the given condition. What? How you prove Banach contraction theorem? Cauchy. How you prove Cauchy's? First you will start with distance between
xn minus
xn and
less than xi.
no, that will come little later. To start with, distance between xn.
xn minus 1.
Ah, very good. Xn and xn minus 1 or xn plus 1, anything. Can we use distance between xn, comma xn plus 1. Xn is where? Either in A or B. Suppose xn is in A, then xn plus 1 will be in B. But what is xn by our definition? X naught is any element, T of x1 is T of x naught, x2 is T of x1, like that. So again xn is nothing but T of xn minus 1. Xn plus 1 means T of xn. So distance between xn and xn plus 1 is equal to distance between xn, distance between T of xn minus 1 comma T of xn. Xn minus 1, y is in A means xn is in B. This xn minus 1 B means next will be in A. So we can use this condition. Less than or equal to k time distance between xn minus 1 and xn. Again proceed less than or equal to k square, then you will exactly Banach contraction theorem. Less than or equal to k power n distance between x naught and x1. That's it. Then we will use, then we will go to distance between xn and xm. Less than or equal to distance between xn and xn plus 1 plus distance between xn plus 1, xn plus 2 up to assuming m greater than n. Then use the I mean like each is less than or equal to k power n to k like that. Then k power something is geometric series converges, then you will prove that distance between xn and xm is Cauchy sequence. Exactly same idea like proving this. That is the sequence xn is a what type of sequence? We can prove that xn is a distance between xn and xm will tends to 0, we can prove. See, once we get that any letter in, whether it is Banach contraction or Kannan type or Chatterjee or many other things, what ultimately will prove is, we'll start with any x naught, we'll start with any x naught from the domain. See, we'll start with x naught from the domain, then x1 is tx naught, x2 is tx1 like that. Then what we are going to prove is xn plus 1 xn is less than or equal to some k, that's a k time distance between xn, x1 less xn minus 1 like that. Then k square time n like that, some k power something, yeah, n minus 1 or okay, n minus 1 something this. Then here it is less than or equal to some constant. Then this we cannot this stage, then we use this is inner. Once you prove this is k okay, like k power n into some fixed number, not variable. Then using that we prove it is a Cauchy sequence. Then that converges, whether it is Kannan type, Banach contraction, we do the same thing. Immediately we will be able to prove this. Then that will become a Cauchy sequence, completeness, it converges. Then that point is a fixed point. Only what is important is, as Professor Verinde mentioned many times, what is the beauty of that is not the proof. Kannan, when you prove this result, the important thing is it's a it is not a continuous map. But proof is essentially same. Even the Chatterjee also essentially same. Many other things, again that inequality you have to use properly. So idea is same. But still they are all important and has nice application. That's why Professor Verinde has given many nice algorithm and many interesting examples. So here we prove that in our case, what is our x2n belongs to a n02. x2n belongs to a, in this case, with this condition, maybe x2n belongs to a, it belongs to A, x2n plus 1 belongs to B. What type of sequence xn? This is x2n is nothing but subsequence. x2n plus 1 another subsequence. What is the original sequence? It is xn, it is a convergent sequence. Suppose xn converges to x. What will happen to the subsequence? It converges to the same point. So x2n also converges to x, x2n plus 1 also converges to x, that means x belongs to intersection. In the beginning we don't assume that A intersection B is non-empty, no contradiction. That implies we cannot separate. Under the contraction condition, under this condition, this implies A intersection B is non-empty. Then once A intersection B is non-empty, you can consider T of A contained in B, T of B contained in A. What is T of A intersection B? Contained in A also, T of A intersection B contained in B also, T of A intersection B contained in A intersection B. Our vector, now our metric space is A intersection B. A and B closed, A intersection B also closed. So T from complete metric space. Closed subset of the complete metric space is complete metric. Now it is nothing but Banach contraction theorem we can use. So what is important thing here is, we don't assume that A intersection B is non-empty. Here our aim is to prove A intersection B non-empty, that's all. Fixed point existence is proved by Banach. We will then, motivated by this, suppose we have in single case like R2 itself, we will forget about contraction also, we will see. So this is 0 0 x 0 y 1 1 0 1 1. A is this. What is A is? X coordinate set of all 0 y 0 less than or equal to y less than or equal to 1. Capital B set of all 1 comma y such that 0 less than or equal to y less than or equal to 1. Now I do exercise. Can you define a map T from A to B, B to A? Satisfying that condition, we cannot say the distance between T contraction type, because now they are what type of set? Disjoint. Suppose distance between Tx, Ty, suppose Rx is a K, 0 less than or equal to K less than 1, so the distance between Tx, Ty less than or equal to K time distance between xy, or x in A, y in B. Then of course they are assuming that R2 in this case. They are all closed subset of complete metric space. Under that condition, we have proved that A intersection B is non-empty. So, but here they are disjoint. Elements in translate, all are migrated from A to B. Okay, here A to B, similarly B to A, here we can define A to B or B to A. Then we don't want this condition forces for x in A, y in B, forces to, this will imply this intersection is non-empty. But this type of situation, can we expect a fixed point? Is it possible? We cannot expect. What is the next best thing? In particular, distance between A and B may be, it should include the original case. We don't assume that in general A intersection may be empty or may be non-empty. Okay? We are assuming even closed compact set under suitable condition, distance between A comma B may be positive. Here positive. Then it is almost like a contraction type. So this will, after T we will come and discuss. Distance between Tx, Ty minus, I write 0. K time distance between xy, anything wrong? 0 is nothing to write, no? 0 we can write, no? Nothing wrong, no? Can you replace 0 by distance between A comma B? This is a contraction. Suppose distance between A comma B greater than 0, then what we see from this, we subtract distance between A comma B. So this distance between Tx, Ty less than or equal to, minus distance between Tx, Ty minus distance between A comma B, sigma is 0. Then this is less than A times between xy minus distance between what should be A comma B. That in particular will be 0. So this is 0 imply usual contraction. If they are separated, then this we call it, what we call it, cyclic contraction. In fact, the earlier one we just informally discussed with Professor Kerr, and he felt okay that we can, because that time these people have not used this concept T of A subset of B, T of B subset of A, like contraction type. There itself they call it cyclic. That's what many have done. But what we realized is they can be separated. So motivated by this concept we introduced in 2006 jointly with my student Anthony Eldred, and that appeared in Journal of Mathematical Analysis and Application. The first one is with Professor Kerr and my another student Srinivasan, that appear in Journal of Fixed Point Theory, which comes from Cluj-Napoca. Okay, after T will continue. Come with a doubt or you can ask.
Any doubt?
Yeah, feel free to.
Yeah.
That's it. If you are not asking, then I will ask.
Yeah, definitely. Then we sit and this stand. See, beauty of this is Professor Kerr and I met most of the stalwarts in mathematics. I am fortunate in that manner. So even I met Billy Sims,
Yeah.
as well as Kirk also, and Billy Sims and Kirk are very good friends. Kirk is from US and Billy Sims from the Castle, Australia. So actually here the issue is you have fixed points. Okay, so they are discovering the fixed points where normally you say that the distance between 2 points is 0 if they are coincident points. But here they started with the distance may not be 0, right? Then only such condition has come, the proximity, something like that. Yeah. So that manner actually the cyclic contraction has come, like you have a map, the image of A is in B and the image of B is in A back. Okay. So that way this is highly interesting, and recently one of my student who awarded PhD, her whole thesis is with the proximity points.
Oh, that.
And you are the god of that thesis because a lot of your all fundamental papers are used in that. But one thing is, for every research paper we have given the applications, either in differential equations, integral equations, or some other. Not in game theory, we have given the applications of the proximity point. So this is also a good thing. Normally we are very much strict to only the fixed point that Tx is equals to x, and we say that is a fixed point. But what happens when Tx is not equals to x? Your assumption is from Tx not equal to x, right? Yeah. So any question? Yeah, that's why. So A intersection B, A union B, okay. A intersection B is shrinking.
Yeah, that time Kaifon was the problem.
Yes, Kifan, yes. Kifan has introduced that, and I think he will now speak about the multi-valued maps, and the first paper in multi-valued map in specific journal of mathematics. So that multi-valued map.
No,
Pacific Journal of Mathematics appeared first
not
time.
your paper.
No, not yours, not
Oh,
yours.
Original.
No, original paper that appeared in Pacific Journal of Mathematics might be 1967,
I don't know.
around,
Yeah.
around, yeah, yeah.
Mainly the
See,
motivation, not very advanced level.
yeah.
How to get multivariate map to use in the existence of non-sequential.
Now, first of all, you have to understand what is a single valued, what is a multi-valued, and what do you mean by a normal map also. Because you should have the very good clarity. That's why I said you come with some sort of mind that, okay, professors or our experts are going to speak about such things, and out of those things, what I know and what I need to know. That is very important. So this kind of curiosity is important, and that you have to develop. See, not necessary you do research and obtain a PhD degree. Everywhere you require some sort of research. Even you do any job and some conspiracy is going on against you, how do you identify that this conspiracy should be shutted out? You need some research. Okay? So I think our food is giving very good sleep to everyone, right? Few of you are sleeping very nicely. Our food is giving very good sleep. So I will say that food should not be that level. It should be little bit reduce the quality. So anyway, if no question, I think we can check out whether tea is ready or not, and we shall meet at 4 o'clock. Okay? Thank you.